Okay, so hi everyone. Today I'm going to be quickly walking you through what I'll be doing for the first chapter of my PhD, which will be looking at the evolution of termite anti-predator defences using a comparative phylogenetic approach. So as most of us know, termites are a social insect group belonging to the order Blattidae or the cockroaches. So they have about 3,000 species worldwide and exhibit great diversity in terms of morphology, habitat, and nesting and foraging habits. So we can see the different morphologies of some termite species on the left here, with the mandibles in particular being highly modified between different taxa. So with a specialised caste system, we see different groups taking on different roles within the colony, and it's the soldier caste in most cases that's responsible for the colony defence. And given that termites are susceptible to a wide range of vertebrate and invertebrate predators, it's no surprise that we see so many different anti-predator defences among termites. So termites create a variety of nest structures ranging from towering mounds and arboreal nests high in the canopy to networks of galleries and tunnels in wood and soil. And a termite colony's first line of defence is the nest structure itself. So hiding away within these nests and galleries reduces the likelihood of being detected by predators in the first place. But what if a predator does come across these termites? So the soldiers in particular have evolved an arsenal of mechanical and chemical weapons to defend against predators. And mandibles in particular are highly modified in different groups to suit different defensive purposes. So you have mandibles for biting and crushing, as well as mandibles for snapping, piercing, and slashing. But in some groups, mandibles are reduced or lost completely and have been replaced with an elongated snout known as the nasus. Chemical defense often accompanies these mechanical defenses, and in some cases, some species rely on chemical defense only. So as we can see in the figures on the screen, the soldier morphologies are very diverse and they're suited for a range of different defensive purposes. And this is probably depending on the predator of these species. So why should we care about these termite weapons? So the sheer diversity of anti-predator adaptations that we see in termites provides a fascinating avenue for exploring the evolutionary history of such a complex social insect. But currently, most of the literature regarding termite defences focuses solely on morphological or chemical aspects and rarely takes behavioural traits into consideration. So given that most of these defences utilise some form of behaviour to sort of release the mechanical and chemical defence, we're not getting the whole picture by neglecting the behavioural defences in our studies. So therefore, we need to look at the defensive system as a whole to be able to understand how these complex anti-predator traits have evolved. We also don't fully understand what has actually driven the evolution of such an array of defensive tactics. So for this chapter, I aim to collate all available literature on termite defences, including morphological, chemical and behavioural traits, in order to describe the evolutionary patterns of these defences and their components, as well as assess correlations with ecological and biotic variables. So I'll be mapping these traits onto a phylogenetic tree that we'll be creating to illustrate the relationships associated with defensive traits and generate hypotheses about their evolution. Specifically for this project, we're going to be looking at how strong the phylogenetic signal is in termite anti-predator defences, as well as looking at whether both nest type and predator diversity correlate with these defensive traits. So we did our big literature search and ended up with about 300 articles relating to termite defence. And I've been very slowly extracting the data, which ends up in this massive big table. It's very slow and tedious to go through, and I'm still currently working through it. Then we're going to map the data onto a tree, and then we're going to collect abiotic and biotic data such as rainfall and climate, as well as predator diversity and nest type using BioClim and GBIF databases. Then once we have all that information, then we're going to throw a whole bunch of phylogenetic analyses at it. And these include estimating the phylogenetic signal of traits using Pagel's lambda models and PhyloANOVAs to test for evolutionary correlation between anti-predator defences and nest and predator diversity. So what do we expect to see from this study? Well, when we're looking at the phylogenetic signal of traits, we expect that the chemical and morphological traits will have a strong phylogenetic signal, whereas behavioural traits are more likely to be phylogenetically labile. We also expect to see termites that have nests that are more susceptible to infiltration by predators, as well as those that have a higher level of predator diversity to possess more sophisticated weapons compared to those who don't. And without having gone through all the literature at the moment, it's a bit hard to work out if there are any patterns that we see in the trait data. But the most obvious thing that we've seen so far is that there's a definite bias towards chemical studies, but very few look at defensive behaviours in termites. And this is something that I hope to contribute a bit more towards throughout my PhD. Here go, that's me finished.